Great. It was great to hear from Geoff Henshaw about NO2 electrochemical sensors. Well, now we're at the point in this webinar where it's kind of more of a question and answer period. What we're going to do is take the questions we've seen on the chat, and just kind of pose them to any of these three different speakers, and hopefully we'll be able to see some questions and concerns that cut across all of these disparate presentations. So we'll just start with Lekan Popoola first. Kind of a general question. Yeah, I guess you can put on people's faces. Super. Kind of a general question. How do you calibrate or validate the data in areas where there are no reference monitors? And how about we could just stick with that if there's no reference monitor?
I think that'll be tricky to do because the whole basis of using this low-cost sensor is to assume you have a reference monitor. So what you can do in that case is to use pre-calibration information. So prior to deploying the sensors, you can actually use information from when they were co-located with some reference monitor. But what you can do is you can actually calibrate them relative to each other. And in those kind of environment, what you can do with the information you have is just to look at the local enhancement. So you would actually not be reporting the absolute value, but relative change to a nominal background. And that is very informative because you can actually characterize or calibrate the signal, but the absolute amount might be off because you don't know what the nominal baseline is. So it'd be good to have a reference monitor at the local site, but if you can't, what you can do is to come up with a way of reporting your data set in such a way that it's just giving a relative magnitude change.
Wonderful, wonderful. Actually, I'm going to pose that out to Carl and Geoff as well. I think this is a kind of a global issue. So again, how can you calibrate or validate in areas where there are no reference monitors? Carl, how do you?
Yeah, I would agree. I would definitely agree with that. First off, ideally you would have a reference monitor, even if you can't have one there constantly. Maybe set up for a couple of months, do your calibration, and then the reference monitor has to move on, but you have this calibration, and you hope it will apply into the future. And then also, as was mentioned, using just qualitative differences between the raw signals. Another possible future approach, which is, I think, not feasible yet, but maybe something that can be done in the future, is to use, satellite retrievals as a way to get kind of a background level of pollution in the area where your monitors are, and then kind of try to get your long-term averages to match up with the satellite long-term averages, and then use your local monitors to get the local contributions in addition to that. The difficulty there is that a lot of the satellite products they require ground data for validation themselves. So they can't, just by themselves, they're not, at the level yet where they can be used as a baseline for calibration, but maybe in the future that'll be another option.
Super. And Geoff, you want to weigh in briefly as well?
Yeah, just wanted to make a really good point. So I just wanted to make another one, and that is that I think we need to get past the point of just thinking about low-cost sensors and regulatory or reference instruments. I think there's room for a hierarchy of types of instruments in which you might have some regulatory, some non-regulatory, and some low-cost sensors. And our work that we've been doing with the University of Auckland has been to develop frameworks which can use different types of proxies to build up a way of building trust in the data coming from these instruments. So yeah, a blended approach, I think, is the way to go.
Great, thank you. It's great to hear all of your different opinions. They're really varied, and that's super. But there are a lot of things that are common as well. Another question, this is more aimed at you, Lekan, which is, I'm going to try to paraphrase this. It says, non-locally, you can't simply use non-local data as your shared baseline, because that doesn't prove that it comes from offsite, rather than from a specific site, namely Heathrow. So how do you actually determine?
So,
Yes.
yeah, I think that, well, that's an interesting question. And I think to answer that question, I'm just going to look at it from a hypothetical point of view, because the whole point of the study at Heathrow Airport itself is that we have a very high dense sensor network. So we're looking at roughly around 40 sensors within an area that's around, well, just covering within the airport perimeter itself. So it's a very, very small area. And instruments are actually sampling every 20 seconds. So I think my hypothetical answer to that question would be, if Heathrow wasn't there, so you don't have Heathrow Airport there, but you still have the same 40 dense sensor network covering that small, let's say 1 kilometer squared area, then, and you allow that, you take measurement at 20 seconds for almost a month, you'd expect all the sensors, if they're all calibrated, to actually respond at 20 seconds to all capture the same variation. And that variation would be coming from what's happening outside that vicinity itself. So now let's now flip it back and assume that you now bring in the airport, which is going to be a local source of emission. The challenge there would now be, how do you disentangle the signal coming from the airport itself relative to what's not airport? And that's where having the high temporal data sets is important, because what you can do with that is, say for every 20 seconds, for every 20-second time step, you have 40 different measurements across all the network. And at one instance, you would have a fraction of those sensors that will be experiencing very low concentration. So, and that low concentration is what you pick out, because that would not be characteristic of emission in the airport itself. Then you go to the next time step, you do the same analysis, look across all the whole network and pick out the lowest fraction. And when you roll that out, what you manage to do is that different components from all the nodes will give you different low values for a different time window. And that would be a representative of what's happening outside the the region where you're actually making your dense measurement. So the key thing there is that you have a dense sensor network, and also you're actually making the measurement at high temporal resolution, because if you're making the measurement, say at an average of 1 hourly value, then you would not be able to disentangle the local emission coming from aircraft itself. But because you're making very fast sensor response measurements, you'll be able to disentangle those two, the high frequency signal coming from local emission from what's non-local. And because you know that you can pull out these two signals, most of the emission around the vicinity of that airport itself is coming, well, it's non-local. And by combining the meteorology with that, we can actually see that it's mostly dominated by wind coming from northeast, which in this case is pointed towards London Heathrow. I'm sorry, central London. And we know that most of the outdoor ambient concentration in London is dominated by traffic, with a small fraction from residential. So I hope that answers the question. And we've actually published the method in atmospheric journal. So if you want, I can point you to that. I think I posted that in the chat as well. I hope that answers the question.
Yes, for a lot of these questions, I've seen that the presenters and others have been posting responses. So that's good. Keep sifting through the chat box, if all of you would. You'll see a lot of answers from the community at large. So Carl, I'm going to turn to you a little bit more. What are the main contaminants that are detected, and what are the sources in sub-Saharan Africa from your experience deploying the ramps?
Yeah, so I would say some of the major sources are roadway emissions. So the vehicle fleets tend to be older and not as the emission standards are not as high as they are in Europe and North America. So emissions. So that's CO, NOx. Also burning, both agricultural burning, which is kind of a seasonal phenomenon that takes place, as well as burning for domestic cooking. So that's a major source as well. And I would also say kind of a more regional source would be dust during dry seasons, especially in Rwanda. We saw there are major contributions from regional dust during the dry season.
Excellent.
So that would be like a PM contribution.
Thank you. Another question for you has to do with what kinds of ramp sensor errors do you contend with? I see you put some message in the chat box, but this is a common issue. So how do you deal with that?
Yeah, so I would I guess, generally categorize the errors into three categories. So the first would be sort of a mechanical or a failure of the sensor itself. This can happen either you have a bad sensor from a manufacturing defect, or over time the sensor response tends to degrade. So this is something we have tried to the best of our ability to sort of detect automatically with some of our routine checks. So for example, if the raw signal from the sensor is not changing very much over a long period of time, that's something that you can kind of detect by analyzing the raw data and hopefully flag that for follow-up. So those kinds of, those are, like, I would say, hardware failure errors. The second source I would characterize as a noise. So, and this is related to the cross sensitivity of these electrochemical sensors to different gases. So, they're picking up on another chemical species which they're not designed to pick up on, but they do. So these kind of cross sensitivities, we try to correct for them as best we can by the calibration approaches we take. But no calibration approach we found is perfect, so there's some noise is going to creep into the signal there. And then the last I would say was sort of a bias. You can characterize this as a long-term kind of a bias term. So and that's really related to the calibration and how appropriate the calibration is to the specific environment that the sensor is deployed in. So if we calibrate in one season and we're collecting data in a different season, we might get a bias because the sensor is now subject to different temperature and humidity conditions and it's responding slightly differently, and there's a systematic difference in the output. So those are the three kinds of general errors I would say we deal with, and there are various ways to solve them, which we discuss in our papers, and you can go there for more details about that.
Great, thank you. I'm going to turn now to Geoff. A couple of questions for you. First, someone asked, does NO2 performance vary across the concentration range? Is there a distinct low detection limit?
Yes, there is a detection limit, of course, and it's on the order of a few ppb for NO2 sensor, electrochemical sensors. If you've got good electronics and some good calibration. There's been some work done on looking at detection limits, and there's plenty in the literature. I didn't understand the first part of the question regarding the concentration range. I mean, the output from these electrochemical gas sensors are largely linear, which makes their data handling quite, quite straightforward.
Very good. And another one here for you is, we noticed similar NO2 patterns in our local measurement, and it's interesting to know the reason that the noise can be so much bigger than the signal. So how do you still use that data and figure out what the actual signal is? Especially related to local sources,
So firstly, these transient signals are quite fast, and they're responding to very fast changes in temperature or humidity that's driving them. And these effects will be seen for most electrochemical sensors, actually. So it's a phenomena which we think is due to changes of this liquid solid gas junction in the meniscus region of the sensing electrode. So it should be a general phenomena. But they're fast, so that if you're averaging over extended periods of time, 15 minutes, an hour, then you're likely not to see them. And secondly, if the environmental conditions that you're measuring under are relatively stable, you're unlikely to see them. So we've picked them up in California when there's been a wind change going from marine airstream switching through to the desert. So if there's big changes in environmental conditions, then you can expect to see larger transients.
Very good, very good. We only have like 2 or 3 minutes. So what I'd like you to do is I'll think about how people could apply some of your lessons to indoor air quality, where of course there's no reference monitors. So just kind of closing thought from all of you, starting with Lekan, then Carl, then Geoff. Half a minute response, please.
Sorry, I didn't catch that. Sorry. What was it?
How to apply your lessons to indoor air quality.
Okay, so I think for indoor air quality, I mean, one advantage is that you don't really have the high transient that you have for the outdoor, where you have the cycle of Downer cycle, where you have variability in humidity and temperature. So that's the ways. That is in a way actually make these sensors more reliable when you use them indoor, because it's almost a very constant condition. So that's good. And the other thing is that you have more enhanced signal due to indoor, especially for some of these toxic gas species. So you get a large signal to noise ratio, so which actually makes these low cost sensors lend themselves well for doing indoor work. And the good thing also is that you can deploy a reference instrument indoors and calibrate it. So I think they are really, really very viable option for doing indoor studies. And we've done a lot of work in our group on that. So I hope that.
Very good. Carl, just in a couple of sentences, what do you think?
Yeah, I definitely agree with that. I would not try to take one of our calibrations developed for an outdoor environment and apply it to an indoor environment directly. I don't think that would work very well, because the conditions are very different. But if you can develop a calibration for an indoor environment, because the indoor environment tends to be fairly consistent in terms of temperature and humidity, you might actually get better generalization performance for different areas, simply because the indoor conditions are more similar. So yeah, if you can develop that kind of an indoor calibration, I think these low-cost sensors can be used very effectively for indoor air quality measurements.
That makes sense. Thanks, Geoff. Any last words related to this?
Indoor air is really, really difficult. If you're not measuring PM or CO2, then it's really difficult. I think those two measurements are fairly straightforward, but I think the background levels, the VOC levels within indoor air make, measurement of ozone too much more difficult. There's some measurements which are easier, some which are more difficult.
Very good. Thanks to Lekan, Carl, and Geoff for your presentations and your time here.